In this series, we'll be going over the questions from IB Physics Higher Level Paper 2 that was featured for the November 2020 exam session. So let's get started. Number one looks like it's a mechanics question that tests our knowledge on forces, dynamics, and perhaps even kinematics. So if you were to read through the question, notice that words like stationary or hovering motionless implies V equals 0. And if this aircraft is hovering motionless for quite some time, it means this zero velocity isn't changing, so acceleration is also 0. So maybe there's a type of translational equilibrium going on where the net force acting on a object is 0. So usually in this case, the aircraft and package would be weighed down by the force of gravity known as weight. But this is somehow balanced by an equal and opposite force, which we will call the lift force. So the question is also going to test us on how well we understand Newton's third law, the action and reaction pair. Okay, so let's get down to the specifics. State the value of the resultant force on the aircraft when hovering. So when the aircraft is hovering, it means that the net resultant force is going to be 0 newtons. So there may be no forces acting on it, or in our case, there are forces acting on it, but they're equal and opposite in direction, so they cancel out. So when we add the force vectors together, we're going to get a sum of 0 newtons. Next, by reference to Newton's third law, how will the upward lift force on the aircraft be achieved? Okay, so Newton's third law is the law that states that for interacting bodies A and B, there are equal and opposite forces. Stated briefly, it means that if A pushes on B with a certain force, then B pushes on A with the same magnitude, but in the opposite direction. So equal and opposite force. So first we have to identify what the force pair is going to be. So the air is propelled vertically downwards with speed v. So we'll assume that air is being propelled downwards because it's being accelerated by the propellers. So there is a force being exerted on it. So if this air is being accelerated downwards, then we know that by Newton's third law, this air will push up against the aircraft, generating lift force. So if you were to answer AII, we would write something like how the blades exert acceleration or a force downwards on air. Now, according to Newton's third law, we'd have the air responding by generating an equal and opposite force. So this force would be heading upwards, right? So upwards on the aircraft. Or in this case, let's say the blades. So since air is pushing the blade upwards, then we know that this is how the upward lift force on the aircraft is generated. So hence, aircraft is able to experience upwards lift force. Next up, we are to find V. So V is the velocity of the air that's propelled downwards. So we are trying to find this figure right here according to the appropriate number of significant figures. So previously, I just left F as blank, but now we have to use a formula regarding force in order to find V. So usually we talk about force as ma, mass times acceleration. Remember Newton's second law, right? Or we can also talk about this in terms of the rate of change of momentum. So, so far in our textbooks or other questions, we might have dealt it with something like this. So we found the change in momentum by measuring the change in velocity. So this was the standard way of how we found force. But notice that we're not given the mass of air. So it's not like we are having a fixed block of air being accelerated downwards. In fact, what we have here is that the mass of the air is given as 1.7 kilograms per second. So this is kind of like the mass flow rate, which is a common notation when we're dealing with fluids. So whenever we have a liquid or gas, we don't talk about like a fixed block of mass, we have a flow rate because it's not the same pieces or same molecules of air continuously moving down. We have a continuous inward flow of air coming in. And every second we can isolate, say, 1.7 kilograms of air and treat it as like a single body for the time being. So in so when we are using this formula, rate of change of momentum, instead of m times delta v, why not try change of mass per unit time times velocity? Okay, so we're going to use F equals rate of change of momentum according to Newton's second law, and we know that the mass is changing, not the velocity. So so the different so the different molecules of air are coming in to be accelerated to the same velocity. And what's important is how much air is coming in at a time. So what's the mass flow rate? So we know that 1.7 kilograms of air is coming in per each second, and they are reaching speeds of v meters per second. And how do we find v? So we should know that the force being propelled downwards onto the air should be equal to the force of gravity that it should balance out. So this force can also be found by F equals mg. So note that the combined aircraft mass is, don't be misled by this figure, 0.45 kilograms plus 0.95 kilograms. So the package, string, and the aircraft add up to 1.4 kilograms. And we multiply the gravitational acceleration, 9.81 meters per second squared. So this is going to give us roughly, if we use our calculators, around 13.73 newtons. What this means is that in order for the aircraft to stay afloat, the upward lift force has to match the gravitational force, 13.73 newtons. So the propeller has to accelerate air downwards at just the right speed, v, so as to generate a downward force of 13.73 newtons. So we can think of it as plugging this figure into the force right here. So we get a new equation. We're going to say 13.73 Newton needs to be generated by supplying air with a velocity of v. So 1.7 kilograms per second times v, whose units are going to be meters per second. So if we divide 13.73 by 1.7, we can also cancel out the units. So 1 Newton is actually kilograms meters per second squared. So if we divide this by kilogram and multiply the second here, we're going to get a meter per second. So we know that the units are consistent for v. So let's write newtons divided by kilogram multiplied by second. This is going to give our v. I'm just going to switch sides. So v is now going to be around 8.08 meters per second. Since we're given numbers like masses in two significant figures, our velocity should only be until two sig figs as well. So 8.1 meters per second using notations that the IB likes. So instead of the slash sign, we want to use second to the power of -1.